Hi, today we're going to continue some kinematics. I'm going to show you the rest of the kinematic equations. And so to start, let's go ahead and review. So we looked at the position time graph and we saw that the slope was velocity. And so the velocity being the change in position or the change in time, we could expand on that and then manipulate it into a usable kinematic equation. And then we did the same thing with a velocity time graph where the slope is acceleration. And so the acceleration was the change in velocity over the change in time. That was the rise over the run. And when we expanded that, looking at the final velocity minus the initial, divided by the time, after some algebra we came up with v equals v naught plus at. So these were the first two kinematic equations that we used. We're going to go into those a little bit more deeper. And I'm going to give you some variations that we can compare position, velocity, position, acceleration, and then velocity and acceleration with and without time. And so at the end of this we'll go through some examples. Okay, you're going to have to put your thinking caps on for this one. Now recall that displacement, so displacement is the area under the curve. Now we understand that all velocities do not start at zero. So you could start at some velocity and then accelerate over a given amount of time to come to a new velocity. We still have a final velocity here and an initial velocity here and a certain amount of time here. And this rule where the displacement is the area under the curve is still true. And so if I wanted to know the total displacement, I could come up with the formula length times width, meaning the length and the width of this box plus the area of the triangle here, 1/2 base height. Okay? Now, length times width is pretty easy to figure out. We've got t as the length and 0 to v naught as my height. And so t times the initial velocity would be this bottom area. The triangle, 1/2 base, the base is going to be in terms here, t, because it's the same as the length. The height, however, is a little bit confusing, right? It appears to go from v naught to v. And so going from v minus v naught, so if we were to do the subtraction to find that height, that's also the change in velocity. Now I want to be able to plug in over here something with t if I can. I would like to express all of these lengths in the same variable. So I'm going to try to figure out how to show change in velocity with respect to time. Now if you recall from the review that I gave you, the change in velocity was seen in that acceleration formula. So I'm going to try to manipulate this in terms of t. So this change in velocity, I have change in velocity right here. And so in terms of t, the change in velocity is going to be equal to at. And so because this is change in velocity and this is change in velocity, and it's kind of like this a equals b and a equals c, therefore b equals c, right? That transitive property, I think is what that's called. And so what I can do is I can take this and I can substitute it where I would put this. So over here where I had 1/2 base height, my height was equal to change velocity. My change velocity is equal to at, and so I can stick at over here. And then when I go ahead and simplify this, I have the change in position is equal to v naught t plus 1/2. I've got two t's, so I'll stick that at the end. 1/2 at squared. This is another kinematic equation. It relates position change in terms of acceleration and time. Now we can express this a little bit differently. You might see this written as like this. and that's okay as well. So there's different ways to be able to use these kinematic equations. So if you're going to take the average of something, you would add up all of your values, and then you would divide it by the number of values that you added and come up with an average. When we talk about the average velocity, we would say that it's going to be the initial velocity plus the final velocity divided by 2. Now I can simplify this, and I can say that VAVG is equal to 1/2 times V naught plus V. But what about time? There's no time in here. Recall that I had the average velocity was displacement over time. So what I can do is I can set these two equal to each other. And I can simplify and reverse. And I have another useful kinematic equation. Now, one of the things that we're going to find is when we go to use these kinematic equations, what we're going to do is we're going to want to choose the kinematic equation based on what I'm missing in the problem. So you'll notice that there's kind of various combinations of the standard variables. Up here I can relate displacement to velocity over a given amount of time. This one is change in velocity is equal to an acceleration over a given amount of time. This one relates the change in position to acceleration over a given amount of time. This one is displacement with respect to average velocity over a given amount of time. And so these are all very useful if you have time. But what happens if you don't have time? A good strategy in physics is to set equations equal to that variable and then substitute in. It's a very, very common way to do that. And so we're going to go ahead and do that. We're going to combine this one right here and this one right here. This one has displacement, the velocities, and time. And this one has acceleration. So where this has acceleration and this one does not have acceleration, what we're going to basically do is we're going to pull that acceleration into this equation. But when we do that, we're going to lose time as a factor. And so that will become useful for us. And this is your last kinematic equation. So I can relate displacement, the different velocities, and acceleration without time. And that will become very useful as we go forward. So if we add to this a little bit, so here are some rules that I've kind of come up with as I've been doing these kinematic problems. Okay, you're going to choose your equation based on what you need and what you don't have. So when you're reading a word problem and they give you a list of variables, you're going to jot those down, and then you're going to compare them to this list here of kinematic equations. And you're going to choose your equation based on what you've been given, but more importantly, based on what the question is asking, okay? Because a lot of times what you are giving will not immediately go into one of these equations. You're going to have to do a half-step problem to get to one of these equations first. So based on what you need to get for the answer and what you are not given. So if you're going to be missing an acceleration, I would choose this equation. If you're going to be missing the final velocity, but you were provided an initial velocity and maybe you're looking for acceleration, you would choose this one. And this is a hard thing to do, is choose the correct equation, and so it's just going to take some practice. Beware of extra information. Oftentimes you'll be giving too much information, some red herrings, if you will. That's very common of any physics problem. We talk in real world language, and then you as a engineer, physicist, need to tease out what is important and what can I use in order to solve the problem, not necessarily what did that layman give me. Okay? Watch your dimensions. If you are doing a problem that primarily resides in the y dimension, your acceleration is probably going to be 9.8 meters per second squared. But that means if this a is 9.8 meters per second squared, then this is the y dimension initial velocity, and this is the y dimension displacement. And that kind of brings me to this last point. Make sure your variables agree. Okay? And this will become very, very important when we get into this next lesson. We start talking about projectile motion, and you're looking at different points along a trajectory. The point that you pick on the trajectory will give you different variables, and you got to make sure that they all match up, and that's very important. So this is your introduction to kinematic equations. I'm going to stop the video right here. I'm going to create another video for help in solving story problems, and I'll go through some examples. So if you feel like you need that, which you probably do, go ahead and switch over to the next video. Alright, thanks.